The next concept along the evolutionary trends. So this is a video in continuation to your previous videos where we were discussing the evolutionary trends, how the level of the organization increases as the animal size and complexity increases, how the cephalization has helped the animals to be successful inhabitants of the universe, how the embryonic development is different along the timeline of the evolutionary development, starting from the protostomic development to deuterostomic development. Now we are going to discuss about the animal body plan or the symmetry. So the earlier animals which were single cellular and they were rolling or floating type of the habitats, they were more ball shaped or cylinder or a cylinder, not basically ball shaped or sphere shaped. So these were having a spherical symmetry. So the spherical symmetry and the animal can be divided into two equal mirror halves from any side, any plane passing through the center of the body. Right? Whereas the radial symmetry is a little bit different, where the animal can be divided into two equal mirrored halves from more than two planes, not from every plane, right? So for example, the jellyfish that can be divided into two halves from any angle. Asymmetrical animals are those who does not have any symmetry. They can take any shape or any form, like the corals or amoeba. And the bilateral symmetry is the most advanced type of the symmetry that is linked to the formation of the head. So you will notice that all those animals which have a clear cephalization, they must have, or they most of the time they have primarily the bilateral symmetry. So that bilateral symmetry has to do something with the efficiency of the animal movement and sensing using the head in the anterior region, right? So that complexity has also increased. If now you see from the corals, they are asymmetrical, then jellyfish, they are radially symmetrical, then afterwards all the advanced animals are bilateral symmetrical, except a few of them in the higher groups, like in echinoderms where starfish, sea anemone, they have the radial symmetry. But remember that radial symmetry is the secondary characteristic. Their immatures are still the bilaterally symmetrical. Then the body cavity formation, as we have already discussed the type of the different body cavity formations. So based on that formation, animals can be divided into acoelomates, coelomates, and pseudocoelomates. All those animals which do not have a body cavity and the space between ectoderm and endoderm is filled with specialized connective tissue or parenchymal cells are called acoelomate animals, and flatworms are their example. In pseudocoelomates, the body cavity exists, but it is lined only on one side from the mesodermal cells, whereas the other side there are no mesodermal cells, hence they are called pseudocoelomates. Examples are nematodes. And coelomates are those animals which have a totally enclosed internal body cavity which has a layer of mesodermal cells on all sides. In the next slide, you will see. So here you see the type of the protostomic development where the cells fill in the space in between ectoderm and endoderm. So these are the mesodermal cells. So they are filling the space and they keep it filling. They do not die and does not create any space. So these type of the animals are called acoelomates. But if the cells from the middle of this cavity are all disintegrated due to the programmed command of the DNA. So leaving only one layer on one side or underneath the ectoderm, but there is no layer of the mesodermal cells on top of the endoderm. This type of the cavity is called a pseudocoelom, and this type of the animals are called pseudocoelomate animals. But if these cells line the inner layer as well, like in the below diagram here, you see. So this type of the cavity formation is called true body cavity, and their animals are called coelomates, right? These are schizocilous development plan. Whereas in the deuterostomic animals, there would never be the pseudocoelomates or acoelomate animals. The all deuterostomes are triploblastic and enterocilous. Okay, so all all deuterostomic development animals They are triploblastic and enterocylous and coelomates, whereas the protostomic animals could be acoelomates, coelomates, or coelomates. Acoelomates, coelomates, or pseudocoelomates, sorry. Okay. So while summarizing, we have seen all these major evolutionary trends which we will see now in the next lecture, that how these characteristics evolved, at what stage, and why they were evolved. Till then, I will leave you to understand these videos, watch these videos, and get the